Actually, I'm PhD student in Ewha Women's University, and today my presentation is application of meteorology-chemistry coupled data assimilation using GEMS synthetic radiance observations. First, I will introduce GEMS. What is GEMS? GEMS is a UV visible imaging spectrometer which will be onboard Geostationary Korea multipurpose satellite 2B. It has 1,000 channels with 300 to 500 nanometer wavelength range, and temporal resolution is 1 hour. Mission of GEMS is focused on measuring and monitoring air pollutants over Asia region and improving air quality forecast. Therefore, GEMS observation can bring important information for air quality prediction. Atmospheric gases have a complex interaction that are impacted by nature and human sources such as traffic, power generation, industry, and agriculture. Some of trace gases are called air pollutants, and a government wants to monitor, control, and predict it. Therefore, it is needed to develop an air quality prediction of transboundary air pollution at regional scales. Modeling interaction of trace gases with weather requires employing coupled meteorology-chemistry models. The coupled meteorology-chemistry models simulate meteorological processes and chemical transformation jointly. Therefore, data assimilation with coupled meteorology-chemistry models can assimilate both meteorological and chemical observation. However, it is hard due to interaction among meteorological and chemical variables. Also, it implies high nonlinearity and flow-dependent forecast errors. So, our objective is application of meteorology chemistry coupled data assimilation using GEMS synthetic radiance observations. We perform direct radiance assimilation since it is typically used in numerical weather prediction. So it is interesting that evaluating the impact of direct satellite radiance observation in coupled meteorology chemistry model. And it is also important to assess the potential value of radiance from new satellites before their launch. In this study, we assimilate synthetic radiance observations using ensemble-based maximum likelihood ensemble filter with the WRF-Chem model. In order to produce synthetic GEMS radiances, we use a radiative transfer model and high-resolution WRF-Chem forecast that begins at different time from the assimilation experiments. Maximum likelihood ensemble filter is a hybrid method combined ensemble and variational method. It has advantage to flow-dependent error covariance and nonlinear capability. Right diagram show how the system works. First, WRF-Chem runs ensemble and control forecast. Then, forecast error covariance is calculated. Next, observation operator transforms state vector to observation state. It is in this experiment, it is conducted by radiative transfer model developed by GEMS team. Then we get radiance field calculated from WRF-Chem profile. Next, observation operator leads observation and calculate observation increment. And then iterative minimization of a cost function is applied to obtain a solution. After minimization, we can get new state vector, so-called analysis. One of the main mechanisms for improved analysis are cross-variable correlation of ensemble error covariance. Difference between analysis and forecast can be briefly explained by multiplying ensemble forecast error covariance and observations. Cross-correlation term highlighted in blue square illustrated the advanced analysis update in a coupled atmosphere chemistry system. It means meteorological observations have impact on chemistry variable and chemistry observations also have impact on meteorological variables. We perform nature run to generate Jan's synthetic radiance by WRF-Chem forecast, starting 6 hours early, having smaller domain and more fine horizontal resolution than the data assimilation experiment. Synthetic observations are created by transforming to radiances at 5 wavelengths and adding random perturbation to the transformed data run. Right figure shows model domain for nature run and data assimilation experiment. Data assimilation domain covers East Asia, while while nature run domain is a little smaller than data assimilation domain because of a huge volume of WRF-Chem output. Maximum Likelihood Ensemble Filter conducts ensemble forecast with 32 ensemble members and 6-hour assimilation window. Wind, temperature, geopotential, dry air mass, and water vapor mixing ratio are employed for meteorological control variable, while ozone, NO2, SO2, and HCHO are employed for chemical control variable. Nature run and data assimilation experiments are started from different time, and assimilation is conducted on 06 UTC, May 10, 2011. From now on, I will present results of these experiments. First, degrees of freedom for signal. It calculated by the dedication and shows entropy reduction due to observations. In other words, it represents how many degrees of freedom are taken from the system by assimilation. Larger DFS implies a stronger impact of data assimilation, while zero value indicates no impact. Right figure shows DFS valid on 06 UTC, and DFS results are concentrated in middle of domain because of a smaller domain of nature run. Uncertainty is significantly reduced over the domain, especially over the Korea, the Eastern China, and the Eastern Mongolia. Next is analysis increment of chemistry. Figure shows the analysis increment of chemistry control variable, ozone, left one is ozone, middle one is NO2, and right one is SO2 at 850 hectopascal. Same with DFS, analysis increments are concentrated in middle of a domain due to small domain of a nature run. Synthetic observations and meteorological observations have an important impact over whole observation domain, especially Eastern China and Korea. Ozone shows the biggest analysis increment compared to other chemical variables. Maximum change of ozone field is almost 80% of background field, while NO2 and SO2 are approximately 60 and 20% respectively. It is related to channel selection. Most of radiance we use these experiments are in ozone absorption band. And chemistry analysis increment show flow pattern. It implies updated meteorological variables have interaction with chemical variables. Next is analysis increment of meteorological variables. Meteorological variables show adjustment over the nature run domain. Figure shows the analysis increment of left one is wind, middle is temperature, and right one is water vapor at 850 hectopascal. Meteorological variables also show adjustment over the nature run domain, and meteorological variables seems like some correlation each other. One of the main considerations of this experiment is to confirm the impact of cross-correlation between meteorological and chemical variables. We can see the impact of cross-correlation in analysis increment. Figures show analysis increment of wind and ozone. And analysis increment of these variables appear same reason. We can Not, we couldn't say these adjustments are impact of meteorological observation or James radiance observation. However, it seems that they are influenced by each other. Conclusion. Radiance data assimilation system coupled with WRF-Chem is developed and tested for the potential impact of James radiance assimilation to improve air quality prediction. The results showed chemical and meteorological initial conditions are successfully updated by MLEF. James synthetic radiances and meteorological data decrease the uncertainty of the WRF-Chem forecast. Analysis increments suggest assimilation of radiance observations impact on both chemical and meteorological variables. We have concluded assimilation of James radiance and meteorological observations can improve the air quality forecast. Thank you.